A lot of what I'll say strongly reinforce it, and then I'm going to go into some different details about the very, very beginning of the electric vehicle and renewable energy value chain, right? So I've often said that the two places in the full EV value chain that are sort of the least commoditized are the very, very end, where you sell a product to the end user, and that's where Tesla is the best in the world and is probably going to stay in the best in the world. And then the other is the very, very, very beginning, where you find a brand new deposit, because that is actually not even an engineering problem. It's harder than that. It's actually a science problem. And you start with an enormous amount of uncertainty. Let's see, I click forward like this. There we go. OK, so the Tesla master plan, as Drew presented it, is completely worth a read, by the way. He sent me a pre-read a few months ago, and it's fantastic. Is definitely scenario-based. There's ways you can tweak the scenarios, but it's a really great document, and it's available for everybody. KoBold has done sort of similar things, not to the degree of detail or broadness, but specifically thinking about battery materials for mobile applications, EVs in particular. And here's one way to think about it. So here is a composite 2023 electric vehicle. Okay, so we took the average battery size, the average battery chemistry throughout the entire market, and said this is what this car would be like. We'd have a little bit of iron and phosphate in there as well, because LFP are about a quarter of the market now. But we didn't include that because those aren't exploration problems. I'm going to be talking I'm going to talk principally about exploration problems. What this gives you a sense for is so a typical EV, if you were to buy that synthetic car, you'd have roughly 140 kilograms of the key materials, key active materials, and collectively it's about $4,000 worth of commodity value. Over half of that is lithium at the current commodity prices. All of those metals come in very specific minerals, right? And then they have very specific uses in the car. And Drew is 100% right that many of these are substitutable, but they're substitutable in very specific ways because of physics, right? And so there are certain materials that are really, really good at doing specific things. And those are listed here: copper, nickel, cobalt, and lithium. Copper we call the essential electrical conductor because it is only the only more conductive element is silver, and the only closely conductive material that's cheap is aluminum, but it's about half of the conductivity. So for high performance applications, an electric motor is effectively a bundle of copper wire. Copper is essential. Lithium, we call it the essential anode. It's really the essential anode for mobile applications for very deep reasons. It's the third lightest element and the most electropositive element on the periodic table. There's no second one like that. It's really, really special. It does things that the next best is sodium, and unfortunately, for mobile applications, sodium is much, much, much less good. Nickel and cobalt are the sort of combined best cathode materials. They do a little different things, they do specific things better than each other, and they are substitutable, sort of titratable between each other, you might say. I won't go into the great physics here of this, but they make the best cathode materials for high energy density, high rate capability, high cyclability batteries. And so if you take that synthetic car that we made for 2023, and then you say, OK, well, I've got a bunch of mines out there. Well, actually, let's start with demand. You say, I need to provide the world with a whole bunch of other applications that have nothing to do with the energy transition. And then I need to build a global fleet of electric vehicles. Okay, global fleet today, 1.3 billion cars on the planet. By mid-century, that'll probably be somewhere like 2.5 billion. Right? Pick your number. It's going to be more than 1.3 billion. You say you've got to fill all those cars in, and recycling doesn't get you there. Recycling works in steady state, and it will work in steady state. We're going to recycle basically all the atoms, but we got to get there first. So that sets the top line. Then you say, okay, we've got all these mines out there producing this stuff. How long are these mines going to last? What are their known reserves? What are reasonable reserve upgrades over time? That's the gray wedge. Any producing mine will have a finite mine life, so that declines. Then we make the most aggressive recycling assumption we can make, which is that every single atom gets recycled in perpetuity, which is physically possible. It's going to be lower than that for economics, but we think it's going to be very high, actually, in steady state. And so then you end up with a gap. And that's the discovery gap, or the exploration gap. The materials that have to be found, the mass of the material that has to be found, developed, brought to market to build a global fleet of electric vehicles. And if you slap today's commodity prices on, you get to something like $12 trillion. That's the value of material, new materials that have to be found, developed, and produced in order to make a global fleet of electric vehicles. And I think this is about 2.4 billion by sort of mid-century. So that is a serious challenge. If you look at kind of P50 mine production rates, that's about 1,000 new mines, roughly speaking, which people in the industry, that kind of blows their mind. But along Drew's theme of optimism, in the last 20 years, we actually found and developed 200 mines of these four commodities, actually. So you're talking about 5x sort of increase in mine discovery and development rate, which is huge, but also completely achievable. Okay. So everyone around here knows this curve really, really well. The cost of computing is down 10 orders of magnitude, roughly, in almost in my lifetime, which is crazy. And that's given rise to basically how we live our lives today broadly. Moore's law of computation. Well, we've characterized a different law. We call this Eroom's law of exploration. So Moore's law is cost of computation, cost per transistor. Eroom's law is expenditures per discovery, good discovery that turns into a mine. You'll notice that through the 80s, it was actually getting cheaper, getting better at things. This is in constant dollars, of course. We were getting better. And then around early 90s, it inflected. And it's becoming much, much more expensive. The industry is spending more for every discovery that they make. So we call this, anyone get it? Eroom's law? Anyone? It's Moore's law backwards, right? Right. So the industry's been getting less and less good, spending more and more to find the same amount of stuff. So this is bad news. This is bad news. But this is an optimistic talk. But it's an empirical fact, and it's bad. Why is this happening? Okay. There's really two reasons, we think. And you're probably already thinking of the first one. The easy things have been found. What this chart shows, we've got depth. It's like the centroid of an ore body that becomes a mine. And then you have time of discovery. And the colors are the three key mineral systems that produce copper, cobalt, lithium, and nickel. You'll notice that they all cluster right at the surface. Basically, for the last century, with a few exceptions, all the major mines have been discovered through directly detectable techniques. Either they are just in an outcrop, and a skilled geologist just looks at it and says, those are ore minerals we should explore here. Or maybe it's covered with some soil or regolith material, and you can measure through just geochemistry, you can measure an anomalous signal of exactly what you're looking for. But directly detectable at the surface. Over 95% of the producing mines directly detectable at the surface. Even some of those that were discovered at depth in the 60s are sort of the exceptions that prove the rule, because they were follow-on discoveries from other ore bodies that were found at the surface. They were discovered through mining, really. So you may think, maybe this is because they sort of form at the surface, and like we're depleting it, we're done. That's definitely not true. We actually know the geochemistry of how these form. They form in reducing conditions in the subsurface, deep in the subsurface. It's actually the subset It's actually a small subset that get moved to the surface through tectonic and erosional processes. And so that's really good news, because it means if you take an arbitrary depth slice through the Earth's crust, your expectation should be that the areal density of good deposits is going to go up, actually. There's more stuff to discover. The problem is it's just much, much harder to find. That's the problem. There's another reason for Eroom's law. And I'm going to, by comparison, look at the pharmaceutical industry. Makes a lot of money, $250 billion a year in net income, pays a lot of dividends, throws almost all of that money back into R&D. It's an industry that is constantly investing in the future, constantly plowing their profits back into new discoveries. Okay, let's look at the mining industry. Makes a lot of money. Pays a lot out in dividends, a little higher fraction than the pharmaceutical industry. How much does it spend on its pipeline? A lot less. A lot less, and it's actually even worse than that, because of that $13 billion, almost half of it is gold exploration, which in my opinion should just stop entirely. We have almost 100 years of already mined and smelted gold sitting in bullion that would be perfectly fine for electronic applications and jewelry applications. You look at the commodities we're focusing on, it's about $4 billion globally, and most of that is actually copper. Nickel, lithium, and cobalt are about $1 billion collectively, exploration expenditures. That's it. And this is the largest natural resource problem of our time. You can also, you take two independent facts, right? You take the fact that the search space is getting harder, and the industry is not investing very much in just doing exploration, and you wind up with Eroom's law. And exploration is exploration activities itself. It's not inventing new techniques for exploration. It's not R&D for exploration. That you can basically round to zero. The companies have just not been investing in entirely new approaches and new technologies, with some notable exceptions. So what we are trying to do is break Eroom's law by inventing new technologies and techniques to improve the efficacy and the efficiency of exploration at every single step. And you can think of these steps as basically starting at very large length scales and very large uncertainties, and decreasing the length scales and decreasing the uncertainties as you move toward what will ultimately be a mining, ultimately be an economic mine. So if you think about like go from districts to prospects to targets to finally discoveries and resources. If you have a sort of four-step process and you reduce the false positives and false negatives at each stage, then do that combined math, you actually end up with a 10x higher success rate, or a 10x higher. So that would completely nullify Eroom's law if you could pull that off. So how do we do that? So I'm going to give you just one vignette, and then we'll get to the fun stuff, the good discussion. But just an example of how we can improve the effectiveness of exploration. So something we call Bayesian exploration. Right? I'm sure all of you know the difference between Bayesian statistics and frequentist statistics. Generally, fundamentally, you sort of, in a Bayesian mindset or in a Bayesian technique, you start with a prior estimate of your probabilities or your expected values, right? And that's easy to say and actually very, very hard to do formally. But let's imagine, so you have some prior estimate of some exploration target. Let's say make it simple, just make it mass of a deposit. How much metal is in a particular deposit. You have uncertainty, you have a distribution. Now let's say you could make a measurement, but before you make the measurement, you could actually know, you don't know what the measurement's going to be, but you could actually constrain how much it will shift your prior distribution. Just imagine you had that for a moment. And then you could look at alternative measurements. And they would affect the distribution differently. And you would know a priori how much the measurements are likely to affect the distribution, but not what they're going to be. That would be really cool, right? And it would tell you which measurement you should make next. Anyone want to guess which measurement you definitely should not make? 2. You should not make 2, because you don't learn anything, right? Your uncertainty is exactly the same. The goal is to make measurements that maximum reduction in uncertainty per dollar of exploration expenditure. Well, we can actually do this. And you can read all the fancy math, lots of Greek letters and stuff here in this paper, co-authored by our sponsor, by our host, Jeff Cares here. It sums it up in this 2 sentences, or 1 sentence that says that's efficacy of information, that's the formal title we put on it, quantifies by how much, on average, future information reduces uncertainty on some discrete property of interest. Okay, let me functionalize this for you. So what you're looking at here is a giant map, huge length scale. You can see the length bar up in the upper right-hand corner of magnetic, total magnetic intensity measurements. So flown over aircraft, making magnetometers, measuring the Earth's magnetic field at a bunch of places, interpolating that and coming up with a continuous contour of the intensity. Okay? 2-dimensional measurements, right? Magnetometer in space, 2D. And you see up in that eastern corner, you see a kind of just a bright pimple there, something very different, very, very different. Interesting. It's actually a magnetic low. We call it a reverse polarity magnetic low. But it's something, it's an anomaly, whatever it is. Okay, well, we want to understand what's in the subsurface. So we want to take this 2D measurement and turn it into something in 3D. Well, standard industry practice would generate something that we call deterministic inversion. This is, in our view, very bad practice, because this is massively unconstrained, gigantically unconstrained. Think 10 to the 4th measurements and 10 to the 7th parameters in your model. Try to solve a system of one equation and 1,000 unknowns. Good luck. That's what this does. So we don't do this, we do something very different. We call it stochastic inversions, and it was invented in collaboration with Stanford. So what's happening now, I've taken that 2D measurement, and I'm not producing my sort of best guess of what the subsurface looks like in deterministic inversion. I'm solving all possible solutions that fit a particular geologic model, all possible solutions. So I'm fully spanning the aleatoric uncertainty. It just means all the uncertainty within a particular model. And so what's happening on the left is I'm showing these different 3-dimensional bodies of magnetic properties that actually that reproduce the signal that the aircraft saw. The point is this is highly non-unique solution. There's many different subsurface configurations that will exactly reproduce the surface I measure, the measurements I made of the surface, and you cannot tell the difference. You cannot. They're identical. But what you can do is classify the full ensemble of valid solutions and the full ensemble of invalid solutions. You can do that, and that is enormously valuable to do. It requires a lot of thought and a lot of distributed computing, a lot of software engineers, a lot of data scientists, a lot of geoscientists. And then what you can do is you can say, well, I want to probe all of these possible solutions and see in which measurements I could make, in this case, geochemistry along a drill core that you take out, which measurement collapses that ensemble of solutions the most. And that's your maximum EOI. Okay? So in a cartoon format, so here we start with all the subsurfaces consistent with the geophysics. And this is not one subsurface. Each one of those little blobs is a different possible solution, or some subset of them are different possible solutions. That's the idea. So this is like representing the full set. And then you could say, well, I could drill those and measure those two, and that would shift my distributions in some way. Or I could drill a totally different orientation and eliminate a far larger fraction of the prior distribution. Or I could do something really silly and measure nothing. Right? All of those are possible, and we look at millions of possible answers and come up with the measurement, the optimal measurement, the EOI maximizing measurement. And you do it, the one that has the maximum reduction in uncertainty. And so that is how we functionalize this whole concept of EOI. And we've done this. That was actually a real case. It was cool because if you look at the surface anomaly, it's that big blue blob. And the standard practice is like you stick a hole right in the middle of it, right? Figure out the middle. But we're trying to optimize for a bunch of different things, right? And basically, the size of the bubble and the color of the bubble tells you effectively how much information you're going to get in a couple different parameters. And so actually, what you want to be doing is drilling way off to the flank, turns out, in this instance. You would never know that without actually just doing all that work. OK. Now I'm going to zoom way, way, way back out to wrap up and show you my very messy version of Drew's really elegant slide, where he said people think reserves go down over time, and actually they go up. And that's true. This is from a paper we published. It's more complicated, but it's cool. So the horizontal axis isn't time, it's cumulative production, how much you're producing of some particular material. And it's normalized to its initial production. Right? So once you go 1 unit over there, that means you produced all the reserves at the original time. And the vertical axis is the reserves at that later time. So if something is right along the 1, that dashed black flat line, if something just goes right along that, it means production exactly equals reserves added. Exactly. Almost every single commodity is above the line. Almost every single commodity reserve grows as a function of how much we produce of the original reserves over a long time. The insert is oil, because it's off the charts. It's 20x the original reserves in the time series after you've produced 20 times the original reserves, right? So this is back to real optimism. Like, humans figure this stuff out, and we're figuring it out. But it's not just the magic of the market. It's people doing things like inventing new technologies that come up with processes to make it more effective and efficient. So I think we will solve these problems. There's a lot of work ahead of us. I wanted to end in a fun and provocative way. So we do science at KoBold, and science is really hard. And science is really fundamentally about making very clear, falsifiable statements for refutation, right? Making conjectures for refutation that are clear and falsifiable. So I have a prediction, and I'm willing to a set of 3 predictions. I'm willing to offer wagers to anyone. We can talk about it at the coffee break. But I want to predict actually how the battery chemistries are going to evolve over time. Because I, like Drew, am an optimist, and we're going to find the materials we need. So I've got a prediction that personal electronics is not going to evolve very much. Lithium is going to remain the key anode material, and cobalt is going to remain the key cathode material. So these wagers are all for 2035 market share. Light-duty vehicles are going to change. We're going to be using more LFP, but I actually think we're going to surprise on the upside with mixed oxide for light-duty in particular. So I'm going to say 90%, more than 90% lithium is the anode material or the charge carrier, and more than 50% nickel oxide blended layered materials. There's some really advantages of using materials that form layered crystal structures. But for stationary storage, for non-mobile, we're going to get away from lithium, I think. We're going to get away from lithium, and we're going to get away from nickel and cobalt, because you don't need the energy density nearly as much. I think lithium will be less than half by 2035. I think we are going to move to things like sodium or maybe oxygen. And the cathode materials will be things like iron. So I think it'll be iron and sodium dominating there. So I'll leave that out there. Come up to me at the coffee if you want to. Casino's open. That concludes my remarks.